Hello everyone, today we're going to be going over the entire multiple choice section of the June 2019 Physics Regents exam. We're going to be starting with question number 1, which asks us which pair of quantities represent scalar quantities. Right, so the answer to this is obviously going to be number 4. Remember that scalar quantities are quantities with no direction, right, and they're usually units of measure. Right, 1, 2, and 3 are wrong because velocity has direction, right? Displacement has direction. Displacement and velocity have both direction. We need only units, only quantities with no direction. Energy has no direction. Time has no direction, so they're scalar, and they're also units of measure. Right, so let me just zoom in, and here. Number 2 says a sailboat on a lake sails 40 meters north and then sails 40 meters to east. Compared to its starting position, the new position of the sailboat is what? Well, I'm gonna, since I'm dealing with directions, right, I'm just gonna draw a compass, so NE, SW, north, east, southwest. And I'm just going to draw this scenario, right? It travels 40 meters north, right? So I'm going to draw an upwards arrow at 40 meters in the north direction, and then I'm going to draw another arrow 40 meters east, right? That's all. And it's saying that that compared to its starting position, right, it starts here because at first it went up 40, then it went right 40. So compared to its starting position, which is S, right, to its new position or its end point, which is E, the sailboat is what, right? So really, they're asking us to describe its displacement, right? So obviously, the sailboat, we're not comparing its direction. We don't care that it went like this. We care really the distance between that S, that E, that start, and that end, right? So obviously, we can eliminate choices 1 and 2, right? Because its end point is going to be northeast from its start point. If we look at this, that displacement line is going like that. If I put this on my compass, that's in the northeast direction. And obviously, the answer to this is going to be 3, right? Just use the Pythagorean theorem. A squared plus B squared is equal to C squared, right? 40 squared plus 40 squared is equal to C squared. That C is going to be 57 meters northeast, right? Number 3 says a ball is thrown straight upwards from the surface of the Earth. Which statement best describes the ball's velocity and acceleration at the top of its flight, right? So this pretty much applies to anything, but at the top of anyone's flight that's going up, assuming that you're going to come back down, right? Your velocity is going to equal 0, but your gravity is still going to equal your gravity, right? Or your acceleration is going to stay constant, right? So that's going to be choice number 2. Velocity is 0 and acceleration is non-zero, right? Why? Well, let's draw a path, right? If this is our object's path, it's gonna continue going up, but as it goes up, it's always slowing down, right? Because gravity is always acting on it. It's always being accelerated downwards by gravity. Gravity is just a force of acceleration. That's always faced downwards, right? So if your acceleration is faced downwards, you're moving upwards, really that acceleration is just eating away at your speed. And it's going to decrease your speed more until you reach a certain point where it's 0, where your speed is going to be 0 meters per second. But guess what? Gravity never stops, right? Gravity is going to continue eating away at your speed, right? So if it's going to continue subtracting from 0, your speed is going to turn negative. And when your velocity is negative, that means you're going in the opposite direction that you started in, right? We started in a positive direction, right? With a positive value with a direction upwards, right? So if we have a negative direction, or if we have a negative value, that means now we're going down. And remember, if you throw something up, it has to come down. That's why it's down, right? Because acceleration is always constant, right? It's going to be non-zero, but the velocity at the top is going to be 0. Number 4 says, as a student runs a plastic comb through her hair, the comb acquires a negative electric charge. This charge results from the transfer of what? Well, obviously, number 1 and 2 are wrong because you can't transfer protons. You can only transfer electrons, right? And remember that electrons have a negative charge. And if the comb is acquiring a negative electric charge, right, that means that the electrons are going from her hair to the comb, right? If the comb is now becoming negative, that means it's gaining electrons from the one place that's giving it to her. The one place that she can get those electrons from is her hair, right? So it's going from her hair to the comb. Number 5 says, how would the mass and weight of an object on the moon compared to the mass and weight of the same object on Earth, right? So we have 2 different values here. We have mass, right, and we have weight. Now mass is always constant, right? If I weigh 50 kilograms on Earth, right, I'm gonna weigh 50 kilograms on the moon. That's because mass in kilogram is measured in kilograms, and mass never changes, right? The weight of this pen, the weight of a 1 kilogram box, always gonna be 1 kilogram no matter where you are, right? That's a scalar quantity, right? Mass is a unit of measure. It never stays the same, right? So knowing that, I could automatically eliminate choices 1 and 3 because it's saying that mass is less, right? Mass is always constant. And number 2, now we're dealing with weight, right? Weight is not constant. Weight is determined by your mass times your force of gravity. That's all that is, and this is measured in newtons, right? Another symbol for weight is just your normal force, or the force that's acting downwards, right? That is the same thing essentially as weight, and that's mass times gravity, right? So if we all know that the gravity on the moon is less than the gravity on Earth, right? And we all know that mass is the same, right? So the greater the gravity, the heavier you will weigh on that place with that specific gravity. So choice number 2, the mass would be the same, but its weight would be less on the moon. Why? Because the moon has a smaller gravity, right? And if you're multiplying m, which never changes, by a smaller gravity, that weight is going to be different from what it is on Earth, right? So really what you need to get from this is that mass is constant, weight is not. Number 4 would also be wrong because it's saying that weight is constant on all planets, which it really isn't. Moving on to number 6, it says an object is moving with a constant speed in a circular path. The object's centripetal acceleration remains constant in what? Well, here, let me just draw a car, right? This is my car. And here's the centripetal force, and here's the centripetal acceleration, right? Now, think about it. As I'm moving around this track, right, my car is also moving. If I'm here in 1 second, I'm here in another second, my car is gonna be here, right? And now, guess what? Because that car is in a new position, guess where its centripetal force and centripetal acceleration is going to be? Now it's going to be directed rather than being directed towards the left, right? Now it's directed slightly toward the right and downwards, right? NFC. Now they're directed in a brand new direction. What I'm trying to get at here is that an object's centripetal acceleration, right, is always going to depend on where it is on the circle, right? If this is going continuously in a circle, right, guess what? The direction of the acceleration, the centripetal acceleration, is always going to change depending on its position, right? So obviously, it can't be 3, right? Because direction is going to be changing, right? And here we have something with a constant speed, right? And acceleration is a change in speed. If your speed is constant, right, that means that your acceleration is not changing. Your acceleration is remaining 0 the whole time, right? So I just said that because we have a constant speed, right, right, and because we're constantly changing direction, it's our only thing that can stay the same is our magnitude, right? Constant speed means that there's 0 acceleration, right? That means that means that the acceleration is 0. But that still doesn't exclude it from having direction, right? So the direction of the acceleration is always going to be changing, but the value of it is not. It is going to stay the same, right? And magnitude is another word for value. So that's all. Number 7 says, as shown in the diagram below, a rope attached to a 500 kilogram crate is used to exert a force of 4.5 newtons at an angle of 6.5 degrees above the horizontal. The horizontal component of the force acting on the crate is what? So remember, horizontal, same thing as your it's just flat on the ground, right? So really, they gave us this diagram and they're like, all right, well, what is this blue line equal to, right? Now, look what I can do here. I'm given an angle and I'm given a value. I should automatically be thinking about my trig functions, right? Because look what I can do. I could just extend this line and make this into a right triangle, right? And next, now that it's a right triangle and this 45 newtons is my hypotenuse, I could just set up a function, right? If I want to solve for this, and I'm going to use this angle too, right? So if my side is adjacent to this angle, I'm going to use cosine. I'm going to write cosine 45 is going to equal to adjacent over hypotenuse, which is over 45 newtons, right? So 45 newtons times cosine of 45 is going to equal my x component, right? And if you calculate this, put this in a calculator, you're going to get that 1, which is 19 newtons. Number 8 says a spring with a constant of 68 newtons per meter hangs from a ceiling. When a 12 Newton downward force is applied to the free end of the spring stretches a total distance of what? Well, this is dealing with springs, so I'm going to go into my reference table. I'm going to scroll all the way down to where it says something about springs. Let me just zoom in so it's easier for y'all to see, right? So I'm going to be looking specifically at this formula, right? Spring force, or force of spring, is equal to K, which is the spring constant, times X, which is its elongation, right? So here I have F of S is equal to Kx, right? Why did I use this formula? Because it tells us a spring constant, right? It gives us K. So I'm going to just fill that in. F of S is equal to 68 newtons per meter, right? And then it says when a 12 Newton downward force is applied, it gives us force, and it gives us spring force, right? So that's really just 12 newtons is equal to 68 newtons per meter times X, right? And it's asking us the stretch of the spring. And if we look here, the value of X corresponds to the change in spring length, right? Change in length is the same thing as saying just stretching, right? It's how much it changes in length, right? So just divide both sides by 68, right? And you'll get your answer, which is 0.18 meters, right? So moving on to number 9, it says that as a student walks downhill at a constant speed, his gravitational potential energy does what? Well, let's look at what a gravitational potential energy is, right? So here we have two different types of potential energies. We have potential energy and potential energy stored in a spring. Obviously, This guy's just walking. There's nothing to do with the spring, so I'm not going to use this one. I'm just going to use what PE is. I'm going to use a potential energy formula, right? So the potential energy formula is mg over the change in h, right? So mg delta h, or the change in height. And as he's walking downhill, right? What's changing? Well, gravity isn't changing because gravity is always constant on Earth, right? His mass isn't changing, right? He's not getting skinnier as he's walking. His mass is gonna remain the same. So the only thing that's really changing when he goes downhill is his height, right? The height that he's at, right? He's starting off at a position where he has a high h, or a high height, and he's ending with the position where he has a low h, right? So in other words, the amount his value of h is shrinking, right? And if everything else remains constant, right? If m and g stay constant, but his h is shrinking, that means his gravitational potential energy is going to first decrease, right? And because he's walking at the same speed, right, his kinetic energy is going to remain the same. Why? Because if we look at the kinetic energy formula, Ke is equal to 1/2 mv squared, right? Like we said, his mass isn't changing. His velocity is the only thing that's his mass isn't changing, right? We said that, and now that his velocity isn't changing, this v is always going to be the same thing. So this Ke is never going to change in value because his velocity is constant, right? Which means not changing. So really the only thing that's changing is his gravitational potential energy, right? Number 10 says when 150 joules of work is done on a system by an external force of 15 newtons in 20 seconds, the total energy of that system increases by what value? Well, they just said that 150 joules of work was done on a system, right? So that means that the answer has to be 1. Because this 1.5 times 10 to the 10 squared, right, is the same thing as saying 150 joules, right? Right here, they said 150 joules is done on a system, right? Now you may be confused by this part, by an external force of 15 newtons in 20 seconds. That's the means by which that force was done, right? Doesn't matter, right? All that means is that, oh, they applied 15 newtons over a span of 20 seconds, and that equated to 150 joules of work, which was done on the system, which means that they added those 150 joules to the system. Number 11 says a person on the ledge throws a ball vertically downwards, striking the ground below the edge, right? So let's just say he's standing on a building, and they throw this ball down, and it goes splat, and it like, boom. All right, whatever. So he throws it down the ledge with 200 joules of kinetic energy, right? So 200 J of Ke. The person then throws the identical ball vertically upward at the same initial speed from the same point. What is the kinetic energy of the second ball when it hits the ground? Well, it's going to remain the same, obviously, right? Because guess what? Let's look at a kinetic energy formula. Ke is equal to 1/2 mv squared, right? If Ke is equal to 1/2 mv squared, and he's throwing the same ball, right? The same ball from the same initial speed, right? So he throws an identical ball. Sorry, not the same ball, but an identical ball. What that means is that if it's the same ball as that, it has to have the same mass as the other ball. So it has the same same mass because it's identical, right? And if he throws it at the same initial speed, right, v is going to stay the same. Because this v is going to be the same as this v because he's throwing it at the same initial speed. So his potential energy, his kinetic energy, is going to remain 200 joules. Doesn't matter which direction he throws it up or down in, right? Because he throws it at the same amount of speed, and because the mass doesn't change, the kinetic energy is going to remain constant. Number 12 says, 2 construction cranes are used to lift identical 1,200 kilogram loads of bricks the same vertical distance. The first crane lifts the bricks in 20 seconds, and the second crane lifts the bricks in 40 seconds. Right, compared to the power developed by the first crane, the power developed by the second crane is what? Well, I'm going to go into my reference table. I'm going to search for where it has to do with power. Well, obviously, power is going to be the formula with P, right? And P is equal to work over time, right? So I'm just going to write that down. P is equal to W over T. Now, what is work? Work is force times distance. And they're really, or force times distance, right? So I think that's a better formula. Right, and you're like, oh, how did you know how to do that? Right, because I was given this, right? I was given a force, or you could find the force of this with a distance and power. Literally, all you have to do is just go here and see which one best matches the scenario. This best matches the scenario, right? So if they're being lifted the same distance, the D is going to be constant. And the force of 1,200 kilograms, right, they're lifting an identical load, right? So the load is going to be different. So the only thing changing here is the time, right? And if the second crane takes twice as long, right, you're dividing your power by 40 compared to where the first crane, you're only dividing your power by 20, right? If you divide something by a bigger number, you're going to get a smaller answer, right? So the power of the first crane is going to be twice the power of the second crane, because the second crane is dividing that force by a bigger number, right? The bigger you're dividing something, the smaller your answer is going to be. So that means your answer to this is going to be half as great, right? The first crane, compared to the power developed by the first crane, the power developed by the second crane is half as much, because you're dividing your force times distance by twice as much. That's all. Number 13 says an ionized calcium atom has a charge of +2 elementary charges. If this ion is accelerated through a potential difference of 2.0 times 10 to the power of 3 volts, the ion's change in kinetic energy will be what, right? So here, we're trying to get, first of all, this is pretty confusing, right? The way that they worded it confusing. But the thing is, my answer, right? My answer is always going to be in electron volts. So I'm going to go ahead and I'm going to look at my first page of my reference table. I'm going to see which units, right, I can use that multiply it back into electron volts, right? So which one of these has a conversion back into electron volts? Well, obviously, this has a conversion back into electron volts, right? It's converting electron volts into energy or joules, right? So I have an idea that I'm going to need to convert these +2 elementary charges into some joules, right? Now, that's one thing, right? Second thing, I'm just going to write down all the units that they gave me, right? So if it has a charge of +2 elementary charges, I'm given charge, right? I'm given Q, just in a different unit, right? And I'm also given V, right? So what it's accelerated through a potential difference, right? So I'm going to go ahead, I'm going to go into my electricity reference table. I'm going to see what has V, what has Q. Well, obviously, this has V, this has Q, right? And you may be asking, oh, what does work have to do with here? Guess what? Work is in joules, right? And we need something to be in joules. So that joules really affirms that I am correct, right? With the formula I'm choosing. So I'm going to write V is equal to W over Q, right? I'm going to convert these +2 elementary charges into coulombs, right? So +2E, I'm going to have to multiply this by, once again, I'm going to have to go back here. One elementary charge is 1.6 times 10 to the negative 19 coulombs, right? So that's 1.6 times 10 to the power of negative 19 coulombs over 1e, right? The e are going to cancel out. You're going to get left with coulombs. I'm going to use this value, right? And then I'm going to set up the equation 2.0 times 10 to the power of 3 volts is equal to an x amount of work divided by 3.2 times 10 to the power of negative 19 coulombs, right? Then I'm going to solve for my work value, right? Which you can do on your graphing calculator right now. And whatever I get for that value of work, I'm just going to convert that back into electron volts, right? So I'm just going to multiply my work value by 1 over 1.6 times 10 to the power of negative 19, right? Because if I have a value in joules, right, I need to multiply that by 1.6 times 10 to the power of negative 19 joules over 1 electron volt in order to get that conversion, right? So all I'm doing, and this is the biggest summary, right? I'm using the formula or the equation V equals W over Q, right? Next, I'm converting my Q, my +2 elementary charges, into Q. So I'm converting them into coulombs, which I'm doing right here. Then I'm plugging in that value for Q. Then I'm plugging in all my values, right? So I get 2.3 times 10 to the power of 3, which is my voltage, is equal to W over my Coulomb charge, right? Then I'm multiplying both sides, and I'm just solving for W. When I get my W value, I'm multiplying it by this factor to get electron volts, and that's it, right? And if you do all of that, you're going to get 4,000 electron volts. So moving on to number 14, it says a total charge of 100 coulombs flows past a fixed point in a circuit every 500 seconds. What is the current at this point, right? So you should know that the current is just delta Q, or change in charge over time, right? So if you have 100 coulombs over 500 seconds, you're going to get 100 C over 500 S, that is 2 amps, right? Number 15 says an aluminum wire has a length of 1.0 meter and has a resistance of 9 times 10 to the power of negative 3 ohms. If the wires were cut into 2 equal lengths, each length would have a resistance of 2. 1.4 times 10 to the power of negative 3, right? All you're doing, remember that the longer the wire, the higher the resistance, right? So the longer your wire is, the higher resistance. If you're cutting this into 2 equal pieces, that your resistance is going to be halved, right? Because the formula is R equals PL over A, right? If you're having this A, if you're dividing or you're making this L smaller, everything else is going to be smaller, right? If you're cutting this wire in half, right, you're making L 0.5 really. And if L is 0.5, R is 0.5. 9 divided by 2 is 4.5. Number 16 says, in an operating electrical circuit, a source of potential difference could be a battery, right? Remember, potential difference is voltage. Batteries supply voltage, right? 9-volt batteries, 18-volt batteries, that's all. Number 17 says, a light bulb with a resistance of 2.9 ohms is operated using a 1.5-volt battery. What is the rate of electrical energy transformed in the light bulb, right? Electrical energy. So we're going to go ahead here and we're going to look for a formula that says that requires electrical energy, right? In other words, we're asking us for the formula for work, right? Or actually, work, which is electrical energy, or we can be using the P, which is electrical power. Same thing, right? They don't give us time, right? So we're going to use P because W involves T, right? So we're just going to use power. We're given resistance and volts, right? So we're going to use P is equal to V squared over R. P equals V squared over R. Plug in your units and just execute it into your calculator. You're going to get 0.78 watts. Number 18 says, as a 40-kilogram child exerts 100 Newton force on a 50-kilogram object, the magnitude of the force that the object exerts on a child is 100 newtons, right? Remember Newton's law. Every action has an equal and opposite reaction. If the child pushes the cart with 100 newtons, the cart is going to push back with 100 newtons because every action, right, that pushing action, right, has an equal, right? So if you push with 100 newtons, the equal, right, has an equal reaction, right? So it's going to push back 100 newtons, right? And equal and opposite, right? So the direction is going to be reversed. So if you're pushing with 100 newtons, the thing is going to push back with 100 newtons. Moving on to number 19, it says two identical stationary bar magnets are arranged in the diagram below. What is the direction of the magnetic fields at point P, right? Remember that magnets travel from north to south, right? So really what you're going to have is this. So you're going to have a bunch of lines that really just go in from the north to south direction. I'm going to draw them here, right? And if you draw enough of these, but you're going to notice, right, I'm just going to go ahead. I'm going to draw the, yeah. What you end up noticing is that this P is right next to these lines, right? That are actually pointing toward I guess southwest, right? They're going to be pointing downwards, right? Yeah, they're going to be pointing downwards. I don't know, my mic cut out. That's all. Just draw the lines, right? Which really, if you're confused about the direction of how the magnetic field flows, draw a picture of the Earth, right? Here you have a North Pole, here you have a South Pole. You know that the and then you know that the magnetic poles are actually flipped, right? So the magnetic North Pole is at the bottom, magnetic South Pole is at the top. You know that it flows from north to south, right? If you flow something going from north to south, really, once you draw enough of these, you're going to see that the electron or the electric field, sorry, the magnetic field is going to be facing downwards. Moving on to number 20, it says a student claps his hands once to produce a sudden loud sound that travels through the air. This sound is classified as longitudinal and mechanical, right? Remember that sound is longitudinal, right? And sound is also mechanical because you need to move in order to produce it. Number 21 says a student generates waves in a pool of water. In order to increase the energy carried by the waves, the student should generate waves with a, number 1, greater amplitude, right? Remember that amplitude. Higher the amplitude, higher the energy. Right, that's all. Moving on to number 22, it says a wave generator produces a straight parallel wave of fronts in a shallow tank in uniform depth water. As the frequency of the vibrations increases, which characteristic of the wave will always decrease, right? In other words, as F goes up, what will go down? Well, obviously wavelength has to go down, right? Because in a wave generator, it produces waves with a constant speed or a constant velocity, right? And if we want to find the formula for the velocity of a wave, you can go into your reference table, right? I know it off the top of my head. V is equal to frequency times lambda, right? And if this V always remains constant with the wave generator, right? And this frequency is going up, the only way to make V constant, right, is going to actually be to decrease lambda, right? So number 23 says a space probe produces a radio signal pulse. If the pulse reaches Earth in 12.3 seconds after it's emitted by the probe, what is the distance from the probe to the Earth, right? So we have a radio signal. For those of you who don't know, you can go to the reference table, right? Which I believe here, and you get the electromagnetic spectrum, right? If you look here, radio waves is on this table, and what this means is that the radio waves is it's a wave in a vacuum, right? And you know that all waves in a vacuum travel at the same speed. Travel at the speed of light, right? Anything on this table is going to have the same speed. In a vacuum, it's going to travel at the speed of light, right? And if you don't know what that is, the speed of light in a vacuum is going to be this big number, right? So I'm just going to go ahead and write that down: 3.00 times 10 to the power of 8 meters per second, right? So because it's on the electromagnetic spectrum, just know that all of these travel at the same speed in a vacuum, which is the speed of light, right? So it travels at the speed of light, and it's asking us the distance. Well, remember that distance is equal to velocity times time, right? Or speed times time. That's not on the reference table. You should probably know that. Why? Because v equals d over t. So if you want to solve for d, you just have to multiply by t. So you get d is equal to vt, right? So if distance is equal to velocity times time, then you have to do the velocity, which you know is the speed of light, which is this big number, right, times the 12.3 seconds it takes, and if you actually multiply this out, you should get an answer of 4. Number 24 says, the diagram below represents a light ray reflecting from the plane mirror. The angle of reflection for this ray is 70 degrees. Remember that the angle of incidence is the angle between the normal and the incident ray, and the angle of reflection is always going to be between the reflected ray, is going to be the same value as the angle of incidence, right? And that's always going to be away from the normal. Always away from the normal, right? So once again, the angle of reflection, right, is going to equal the angle of incidence, right? So this is the angle of incidence, and this is the angle of reflection. And rather than it being between the mirror or the surface and the ray, it's going to be between the normal. It's going to always be between the normal and the ray, right? So 70 and 70 are going to be your two answers, right? Never ever are you going to have an answer that's 20, right? Always look inside of it. Think of these two rays of light as a book opening, and your angles are going to be inside your book only, right? 70 is inside your book only. Number 25 says, as a light wave travels from one medium to a second medium, with a greater absolute index of reflection, which characteristic of the wave cannot change, right? The answer to this is frequency. Frequency remains constant between all mediums, right? 26 says the speed of light in a glycerol is what? Well, the speed of light, we know that the speed of light in a vacuum is 3.00 times 10 to the power of 8 meters per second, right? And we also know the formula. If we go down to waves, here we know that n, right, our index of refraction, is going to equal to the c, the speed of light over v, right? So if we know that n is equal to c over v, we know that v is equal to c over n, or the velocity of your light is going to equal to the speed of light divided by the index of refraction, right? You can do this by multiplying by v on both sides and then dividing by n, right? So if your velocity or your speed of light in glycerol in a medium is equal to v over c over n, right? V is equal to 3.00 times 10 to the power of 8 meters per second. And we're going to divide the speed by our index of refraction, right? Which we can see in this table, right? Absolute indices of refraction. We're talking about fused quartz, which is 1.46, right? So here we have 1.46. So 1.46 divided by 3 times 10 to the power of 8 is going to be choice number 2, right? So moving on to number 7, it says the diagram below represents a standing wave produced by a string in a vibrating by a vibrating wave generator, right? So how many antinodes are shown in the standing wave? I'm going to zoom out so we have a better look at this. So we have this, right, and it's a standing wave. And know that whenever these two waves actually intersect, right, that's going to be called a node, right? Each intersection point is a node where they cross, right? Now it's asking how many antinodes there are. Well, there's 4 nodes, right? And that has nothing to do with antinodes, really. I just want you to know what a node is. When it comes to antinodes, it's going to be the place where they're most furthest apart, right? So think about it. If a node is the place where they intersect, or the node, and because the intersection is where they're at the same place, right? Because the node is the place where they're closest together, anti means opposite. So obviously an antinode is going to be the place where they're furthest away from each other, right? So that's going to be at this point, right? Because they're furthest away from each other here. That's going to be at this point because they're furthest away from each other here. And that's going to be at this point because they're furthest away from each other here. So really there are 3 antinodes. Number 28 says the Doppler effect is best described by the shift in observed frequency and wavelength of the wave caused by the relative motion between the wave source and the wave's observer, right? All this is saying is that if something is emitting a wave, right? Let's just say this is a speaker on a car and it's emitting a wave, if you're standing here and you listen to it, and you're standing here and you listen to it, you're going to observe a different frequency, right? If you're listening, you're going to hear a higher pitch here and a lower pitch here. There's a difference in frequency. If you're analyzing the wave, you're going to have a higher frequency here, lower frequency here, higher wavelength here, lower wavelength here, right? That's all, right? It's a shift in observed frequency, right? You're hearing at a higher pitch or a lower pitch, and wavelength. You're seeing a bigger wave or a smaller wave caused by the relative motion between the wave source and the observer, right? So if it's coming to you, you're going to hear it at a higher wave. If it's coming away from you, you're going to hear it at a lower pitch. That's all. Number 29 says, which represents diffraction of wave fronts as they encounter an obstacle. 3 and 4 are wrong because this is kind of, I guess, reflection, right? They're reflecting off of it. They're bouncing off of it. Same thing with this one. If we're talking about diffraction, that means that when the light waves curve around something, right? If you they curve around the source of obstruction, that's going to be choice number 1, right? Really, these aren't curving, so that's not diffraction. This is curving because it's diffraction. Now, there's another type of diffraction, right? If they're going through an aperture or a small lens or a small opening, they're going to curve around it. Really, but when you ever see, when you see diffraction, just think about waves curving. That's all. Number 30 says, which type of forces exist between two protons in a helium nucleus, right? So remember that this is going to be a nucleus, right? And inside of them, there are going to be two protons. Now remember that protons, because think about electricity, right? Proton and electrons and neutrons, think about electricity, right? So it's going to be an electrostatic force, right? Because you have two types of things that fall into electrostatics, right? You have protons, and you have electrons, right? You have positive charges, you have negative charges, right? Whenever you think of charges, think of electrostatic force, right? And because we know that likes repel, right? You're going to have a repulsive electrostatic force, right? It's always going to repel. They're going to repel each other, right? So these positive, these protons, right, which are positive, have the same charge. So that means that they're going to try and escape and repel away from each other. But the thing that's actually holding them together is a strong nuclear force, right? That's why particles don't just randomly fall apart. That's because they have a strong nuclear force. Whenever you hear nuclear force, think of a nucleus. This is the nucleus of an atom. Makes sense, right? This is also called strong force because it's so strong that it overpowers the repulsive force. Number 31 says a meson could be composed of what? Well, for those of you who don't know what meson is, it's a particle, and we have a class of, and mesons can be found on this table. This is page 3 of your reference table, right? So here's classification of matter, right? So matter goes into leptons, hadrons, barons, mesons, right? And here, if we see mesons, it's saying that mesons are made of a quark and an antiquark. So we're going to be looking at this table only, right? Which are quarks and antiquarks, right? So let's look, right? Is it saying a top quark and a bottom quark? That's wrong because we need a quark and an antiquark, right? A top and a bottom quark, right? There's no antiquark here. The only thing with the antiquark is a strange quark, right? Strange quark is still a quark. And here we have an anti-charm quark, right? Here we have a charm quark, right? But it's saying anti, and that means it's an antiquark. That's all. Because whenever you have anti in front of something, that means that it's an antiquark. That's all. 32 says an electron is in an excited mercury atom is in energy level G. What is the minimum energy level required to ionize this atom, right? So we're going to go here and we're going to go into ionization or energy level diagrams. We're going to look at mercury, and it's saying that it's in level G. So if it's in level G, right, if you want to ionize it, you're going to have to bring it down to the ground state, right? So what do you need here in order to actually, or what would you need to ionize this to either bring not bring it to a ground state, right? If this, they literally tell, sorry, I made a mistake, right? But this, they say that this is the line of ionization, right? So if I want to ionize this, obviously I'm going to have to reach this level. So what do I have to add, or what do I have to subtract in order to reach that level? Obviously, I'm going to have to subtract 2.48 electron volts, right? Think about it. Negative 2.48 electron volts minus, right? 2.48 electron volts, right, is going to be what I need to ionize it and to bring it right to that level 0, right? Nothing else here is going to actually be enough to bring me to that specific level of ionization or ionize me, right? Obviously, it's not going to be 7.9 because, yeah, it does bring you above it, but I want to be exactly at this level, right? So negative 2.48 plus 2.48 is 0. So that's all. Moving on to 33, it says a student is standing in an elevator that travels from the first floor to the 10th floor of the building. The student exerts the greatest force of the elevator on the floor of the elevator when the elevator is what? Well, obviously, it's when the elevator is accelerating upwards. Because think about it. If I'm standing on this platform, and this platform is accelerating upwards, it's moving upwards, right? My inertia which is my tendency to stay to not move unless a force is acted upon me, I'm going to be pushing down this elevator. I'm going to be pushing this elevator downwards, right? I'm going to be pushing it downwards. That's why whenever someone pulls you, whenever an elevator is really starts accelerating upwards, or anything starts accelerating upwards, you start being pushed back down to it, right? Because you want to stay out of motion, and that acceleration or that force being applied is bringing you out of motion. That's all, right? If you're slowing down, that means that you're actually going upwards, the force is upwards, and if you're moving upwards away from the floor, that means that there's less force on the floor. If you're moving upward at a constant speed, that means that there's no force being applied to you, right? Same thing at rest, at moving at a constant speed, there's no forces applied to you, right? So if the force is pushing you upwards, right, that means that you're being really pushed downwards, because your body wants to stay not in a state of non-motion, right? Number 34 says at the bottom of a hill, a car has an initial velocity of plus 16 meters per second. The car is uniformly accelerated at negative 2.2 meters per second squared for 5 seconds as it moves up the hill. How far does the car travel in this 5-second interval? Really, all you need to do here is remember, you got to go into your reference table and see which formula gives you VI, which formula gives you A, which formula gives you T, and which formula gives you D, right? So which one has VIATD? Obviously, it's going to be D is equal to V initial time plus 1/2 AT squared. This is the only formula. If you plug in your values, you're going to get D as 52.5 meters. Number 35 says a particle enters an electric field between two oppositely charged parallel plates, as represented in the diagram below. Which particle will be deflected towards the positive plate as it enters the electric field? Obviously, the answer to this is going to be an electron, right? Because we're saying deflected towards the positive plate, which means that we're moving towards the positive plate. Which one moves? Remember that opposites attract, right? So if you have a positive and a negative, those are opposites. They're going to attract, and you're going to have to actually move up to that positive.